So this is the problem. Can you find all the real zeros of this polynomial function in 20 seconds or less, or close to it? No calculator is allowed. Okay, the time is really up. You had more than the 20 seconds. You can pause the video and continue to try. Then I'll be back with a brief explanation just in case. I'm sure you know what a zero is, but just in case you don't, I'll go through that. So here we go. For any polynomial function, if I evaluate that function at some number k, and I get 0, then we say that k is a zero of that polynomial. If you were to graph the function, and the graph crosses the x-axis, at the points where it crosses the x-axis, you're going to get the zeros. So let's say this function passes the x-axis at some number a, crosses the x-axis at a. Then the y component is going to be 0. At any point where the graph crosses the x-axis, the y value is always going to be 0. So you can find all the x-intercepts to the graph. The first component of those points, the x-intercepts, will generate the zeros. So for example, let's try the polynomial function p1 of x is equal to x squared minus 1. The zeros, again, are the values for x, such that if I replace the x by that number, I'm going to get 0. So basically, I want to know when is x squared minus 1 equal to 0. So you're just solving that equation for x. I can factor that. The difference of squares, x minus 1. X plus 1. So I can see here that this product is going to be 0 when either x is equal to 1 or negative 1. Those are the two values that make that product 0, which of course makes this 0. So the zeros of this polynomial are 1 and negative 1. Whereas if I have a second polynomial, say p sub 2 of x equals, say, x squared plus 4. I want to know when is this equal to 0. Again, if the graph doesn't cross the x-axis, it's not going to have any x-intercepts. And since the first components of the intercepts, x-intercepts, generate the zeros, this one is going to have no real zeros. Now it does have imaginary zeros, because if I write this as x squared equal to -4, take plus or minus the square root of both sides, and I'm going to get x is equal to, and plus or minus the square root of -4 is going to give me plus or minus 2y. So 2y and minus 2y are the zeros, imaginary zeros in this case. It doesn't have any real zeros. So let's get back to the problem over here now. Have you figured it out? Pause the video if you want again. Try it. Okay, there's only one real zero. It should be clear to you, I hope, because every term here has an x. This is a ninth degree polynomial. So the theory of polynomials would suggest that this has 9 zeros. Now it could be imaginary zeros, real zeros. But it turns out that this one only has one real zero. Because every term, I should say, here has an x, it should be clear that if I replace the x by 0, place the x by 0, then I get 0 here, 0 here, 0 here, 0 here. Then the value of the polynomial function is 0. So when x is equal to 0, the value of the function is 0. So 0 is the only real zero. And then you can see here that if I factor out the x, the first term becomes x to the 8th. The next term becomes 8 x to the 6th. The next term is 11 x to the 4th. And the last term is 7. So it should be clear to you that this first term x to the 8th, because the coefficients of each of the terms is positive, and of course the last term is constant, positive constant 7. No matter what number I plug into, whether I plug in a positive number or a negative number, the first term will always be positive. Second term will always be positive. The next term will always be positive. And of course the last term is going to stay 7. So there's no way that I plug in a number in here and get 0. So I have the product of x and this right here. X will be 0 when I replace it by 0. But if I replace all these other terms by 0, I get 7 here. And 7 times 0 is 0. But there's no other number that will make this product 0 other than the number 0. Now this does have imaginary zeros. We're asking for real zeros. So that's the solution to the problem. Thanks for watching. We'll see you next time.